So here you are, in the quiet, in the dark, and the day has finally let you go. And maybe your mind is still turning things over, or maybe you are already half drifting, and either way is fine. There is nothing you need to solve right now, nothing you need to fix, and certainly nothing you need to remember from what I am about to say. Think of the next while as a slow walk through a very old, very beautiful house, the house being your own body, and the walk being through the rooms of the nervous system, the wiring that runs through every part of you. You do not need to take notes on the rooms. You do not need to memorize the layout. You can let the words come and go like someone describing a landscape outside a train window, and if you drift away from the words entirely, that means they are doing their job. The body has a communication problem, and it is one of the oldest problems a living body can have. The brain sits in one place, tucked inside the skull, protected and warm and mostly in the dark, but the brain needs to know what is happening everywhere else, in the tips of the fingers, in the soles of the feet, deep in the organs, along the skin. And it needs to know instantly, or close to instantly, because a delay in knowing that something is hot or sharp or wrong can mean real damage. So the body has solved this problem with a kind of living wiring, a network of long, thin cells that stretch from the brain and spinal cord out to every corner of the body, carrying messages back and forth at speeds that are hard to fully grasp. A signal can travel from your fingertip to your spinal cord and back again faster than you can finish a single slow blink. And most of the time, most of every day and night, this entire system runs without your attention, without your effort, without you having to ask it to do a single thing. This network, this living wiring, is called the nervous system, and the name itself can feel a little daunting because the nervous system has so many parts with names that sound alike, names that overlap, names that were given by different people at different times in history before anyone really understood how the whole thing fit together. So if you have ever heard words like neuron and synapse and myelin and cerebellum and felt your attention start to blur, that is not a failure on your part. The nervous system is often called confusing, but not because it is disorganized. It is called confusing because the words we use for it grew up in a sprawling, unplanned way, like a city that was built over centuries with no single architect. You do not need to master the map. You do not need to remember which street connects to which. We are just going to walk through the neighborhoods, one by one, and I will point things out as we go, and if a name slips away from you, it was never meant to stick. So let us start with the broadest possible shape of this territory, the view from very high up, like looking down at a country and seeing its two great regions. The nervous system has two main divisions, two great chapters in the story we are going to walk through. The first chapter is the central part. This is the command post, the main office, the place where the vast majority of decisions get made and signals get sorted. It includes the brain, which sits inside the skull, and the spinal cord, which runs down through the bony tunnel of the spine. Together, the brain and spinal cord form what is called the central nervous system. That is the first chapter. The second chapter is everything else, all the wiring that leaves the central command post and travels outward, threading through the arms and legs, weaving through the organs, running along the ribs, reaching the skin. This is called the peripheral nervous system, and the word peripheral simply means away from the center, out toward the edges, which is exactly where these nerves go. Think of the central nervous system as the main road, the great highway that runs from the top of the head all the way down the back. And think of the peripheral nerves as the smaller roads and paths and driveways that branch off from that highway, leading to every house and field and distant corner. That is the basic map, a central highway and its branching roads. The brain and spinal cord in the middle, and the nerves reaching everywhere else. And we will spend time in both of these regions, moving slowly from the center outward, and then back again, and then back once more. Because repetition is not a flaw in a conversation like this. Repetition is part of the comfort. A listener who is drifting toward sleep will miss things, and the ideas will circle back, and that circling is gentle and intentional. Now, before we step into the first neighborhood, I want to say something plainly about the way we are going to talk about all of this. The nervous system is full of numbers, and full of names, and full of facts that can sound astonishing if you say them in a certain voice. But I am not going to use that voice. The facts are astonishing on their own, quietly, without anyone needing to underline them. When I tell you, eventually, that the human brain contains roughly 86 billion neurons, I am not going to say it like a fireworks display. I am going to say it like someone remarking on the number of stars visible on a clear night, vast and humbling, and completely indifferent to whether we are impressed. And when the science is uncertain, when the researchers themselves do not fully understand something, and there are many such things in the study of the brain and nervous system, I will tell you that plainly. Not knowing is not a failure. Not knowing is restful. It gives you permission to stop trying to figure everything out and just lie there, breathing, while your own nervous system does what it has done since before you were born. So the first thing to understand, the very first piece of this whole picture, is the single cell that makes all of this communication possible, and that is where we are going to go next. Not right now, but soon. For now, just settle into the idea that your body is threaded through with living wires, that messages are moving along those wires right now as you lie here, that your brain is receiving a constant stream of information from every part of you, the temperature of the air on your skin, the pressure of the bed against your back, the quiet sound of these words reaching your ears, and that all of this is happening without you lifting a finger or forming a single thought. The system runs. It has always run. It will continue to run while you sleep. And sleep, of course, is where we are gently heading. The whole shape of this walk is designed to bring you closer to rest, not further from it. So we will move slowly. We will not rush through any room. We will pause and look around and maybe describe the same thing 2 or 3 different ways, so that if you miss one description, another will catch you. There is no test at the end. There is no destination we are trying to reach. The walking itself is the whole point, and the walking can go on as long as you need it to, and when you no longer need it, you will simply drift away, and the words will become a soft murmur in the background of your sleep, and that is exactly what they are meant to do. I want to return to that idea of the 2 great chapters, because it is worth resting on. The central nervous system, the brain and spinal cord, is the part that makes sense of the world. It receives all the incoming signals, sorts them, compares them to past experience, decides what to do, and sends out instructions. The peripheral nervous system, the nerves that branch out through the body, is the part that gathers the information and delivers the instructions. One part thinks and decides, the other part senses and acts. But even that distinction is too simple, because the 2 parts are not really separate, they are continuous. The nerves in your fingers run up your arm and into your spinal cord, and the fibers in your spinal cord run up into your brain, and there is no clear boundary where one stops and the other begins. It is all one long, continuous tapestry of living tissue, and we are just drawing lines on the map to make it easier to talk about. And talk about it we will, in the sections ahead. We will start with the single nerve cell, the tiny living unit that makes all of this possible. We will look at the way those cells talk to each other across tiny gaps. We will walk through the neighborhoods of the brain, one by one, like touring rooms in a quiet house. We will follow the spinal cord down the back and see how a reflex can move your hand away from something hot before you even feel the heat. We will follow the peripheral nerves out to the fingers and toes and skin. We will spend time with the 2 great modes of the automatic nervous system, the one that prepares you for action, and the one that calms you back down. We will explore how the body feels touch and heat and pain. We will listen to the nerves that carry sight and sound. We will talk about memory and learning and the slow, patient way the brain changes over time. And then we will bring it all back to sleep, to the quiet rhythms that are already settling over you now. But for this first section, the only job is to ease in, to let the shape of the journey become vaguely visible, like the outline of hills in the evening, without demanding that you trace every contour. The words will be here, the ideas will circle back. And you, in the meantime, can let your body sink a little further into the bed, can let your breathing slow a little more, can let your eyes stay closed, and your attention drift wherever it wants to drift. Your body already knows how to do this. It has been doing it every night of your life. The nervous system is not something you need to operate. It operates itself. Right now, as you listen, your brainstem is keeping your heart beating. Your spinal cord is quietly relaying signals. The nerves in your skin are reporting the temperature of the room. The nerves in your muscles are keeping just enough tension to hold your body in its resting shape. All of this is happening below the level of thought. All of this will continue to happen while you sleep. You are not the operator of this machinery. You are the quiet passenger, the one being carried, and carrying is what the machinery does. So let yourself be carried. Let the words become a kind of landscape, a slow-moving river, and let yourself float on it without needing to steer. We are going to start, in the next section, with the smallest living piece of the whole system, the single nerve cell, the neuron. But before we get there, just rest here for a moment. Rest in the knowledge that your body is already doing everything it needs to do. Rest in the knowledge that the nervous system, for all its complexity, is running smoothly and quietly in the background, like a calm and competent crew managing a ship while you sleep below deck. The ship moves. The stars turn overhead. The water is deep and dark and steady, and you do not need to do anything at all except breathe and drift and let the night hold you in its slow and patient hands. So we arrive now at the smallest living piece of the whole picture, the single cell that makes all of this communication possible. The brain, the spinal cord, the nerves that reach into every part of the body, all of it is built from these individual cells. And if we want to understand anything larger, we need to spend some quiet time with this one small thing first. There is no hurry. We are going to look at it slowly from a few different angles, describing it in plain and simple terms, so that by the time we move on to the bigger structures, this small foundation will feel familiar and settled. A nerve cell is a living cell, just like the other cells in your body, but it has a shape that is unlike almost anything else. Most cells in the body are roughly round, or blocky, or flat, compact shapes that stay in one place and do their work locally. But a nerve cell is built to reach. It is built to stretch across distance. It is built to carry a message from one place to another, and its whole shape is organized around that single job. If you could see a nerve cell under a microscope, it would look something like a tree that has been pulled gently in two directions, roots spreading out on one side, a long trunk in the middle, and branches spreading out on the other side. That is the basic image to hold in your mind. A tree with roots on one end, a long slender trunk, and branches on the far end. And the message travels through this tree in one direction only, from the roots, through the trunk, out to the branches, and then on to the next cell. Let us walk through the three main parts of this tree-shaped cell, one at a time, using plain words first, and then giving the proper names, so the names have somewhere to land. The receiving end of the cell, the part that looks like roots spreading out into the soil, is built to catch incoming signals. These root-like extensions reach out into the space around the cell and pick up messages from other nerve cells nearby. They are thin, they are numerous, and they branch again and again into finer and finer threads, which gives them a lot of surface area for catching signals. In the language of neuroscience, these receiving branches are called dendrites. The word comes from a Greek root meaning tree, which makes sense when you see them. They do look like the bare branches of a tree in winter, spreading and dividing and spreading again. So the dendrites are the listening parts of the nerve cell, the parts that reach out and gather information from the world around them. The signals that the dendrites collect all flow inward, toward the central part of the cell. This central part is the cell body, and it looks more like what we expect a cell to look like, a rounded, compact structure that holds the nucleus, the cell's genetic material, and all the tiny machinery that keeps the cell alive. The cell body is the home office. It receives all the incoming signals from the dendrites, and it makes a kind of continuous, low-level calculation. Not a conscious calculation, not a thought, but a physical, chemical summing up of all the signals coming in. If the total incoming signal reaches a certain threshold, a certain tipping point, the cell body decides to send a message of its own, and that outgoing message travels down the third and most dramatic part of the nerve cell, the long sending cable. This long sending cable is the part that gives the nerve cell its remarkable shape. It extends outward from the cell body, and it can be very long indeed. Some of these cables run from your spinal cord all the way down to your toes. That is a single cell stretching nearly the full length of your body. The proper name for this long sending cable is the axon. The axon is built to carry a signal away from the cell body, out towards some destination, another nerve cell, a muscle, a gland. The signal travels along the axon as a brief pulse of electrical activity, a small wave of charged particles moving across the cell's outer membrane. This pulse moves fast, and in some axons it moves very fast indeed, which we will come to in a moment. But the key thing to remember, the simple picture to hold in your mind, is this. A nerve cell has three main parts: the receiving branches, which are the dendrites, the central body of the cell, and the long sending cable, the axon. Signal comes in through the dendrites, gets summed up in the cell body, and goes out along the axon. That is the basic flow of information through a single nerve cell. Now, some of these axons are wrapped in a fatty coating that makes the signal travel much faster along the cable. This coating is made of a substance called myelin, and it deserves a few quiet moments of attention because it is one of the body's most elegant pieces of engineering. Myelin is a pale, fatty material that wraps around the axon in segments, like insulation around a wire, leaving small gaps between each wrapped segment. The signal, that brief electrical pulse, does not simply race smoothly down the whole length of the axon. Instead, it jumps from one gap to the next, from one uninsulated spot to the next, which allows it to move much faster than it could if the axon were bare. An axon wrapped in myelin can carry a signal at speeds of up to roughly 100 meters per second, which is more than 200 miles per hour in more familiar units. An axon without myelin carries the signal more slowly, perhaps only a few meters per second. The difference matters. The myelin wrapping is what allows your body to react quickly, to catch yourself when you stumble, to pull your hand back from something sharp, to process the rapid flow of information that makes up a spoken sentence or a piece of music. Not all axons are wrapped in myelin. Many are not. The ones that need to carry urgent, time-sensitive messages tend to be the ones with the fatty coating. The ones that carry slower, more persistent signals, dull aches rather than sharp pains, or background information about the state of your organs, often travel along bare axons. And the myelin itself is not part of the nerve cell proper. It is made by other cells that wrap themselves around the axon, like someone carefully winding tape around a pipe. In the brain and spinal cord, the wrapping cells are one type. In the nerves out in the body, they are another type. The details of which cell wraps which axon are not something you need to hold on to. What matters is the image, a long cable, wrapped in fatty insulation, carrying a signal at high speed, jumping from gap to gap. Now that we have the shape of a single nerve cell in mind, the dendrites, the cell body, the axon, and sometimes the myelin wrapping, we can step back and consider how many of these cells exist in the human brain alone. This is one of those numbers that is genuinely hard to grasp, and I am going to state it plainly and calmly, without making a production of it. Careful cell-counting studies over many years have arrived at an estimate of roughly 86 billion neurons in the average human brain. 86 billion. That is an enormous number, and it is worth pausing on for a moment, not because you need to remember it, but because the size of it tells you something important about the scale of the system we are walking through. 86 billion individual cells, each one shaped like a tiny tree, each one connected to hundreds or thousands of other cells, forming a network of almost unimaginable density. But I want to be careful with that number, because precision in the wrong places can be a kind of distraction. That number, 86 billion, is an estimate. It comes from careful work, from counting cells in samples of brain tissue and scaling up, but no one has counted every single neuron in a human brain one by one. Brains vary from person to person. Different counting methods give slightly different results. So it is better to hold that number lightly, as a rough sense of the scale we are dealing with, rather than as a fixed and certain fact. The brain contains tens of billions of neurons. That is enough. That is more than enough to sit with quietly in the dark. And here is a detail that will lead us naturally toward the next section of our walk. A neuron does not touch the next neuron directly. For all the complexity of the network, for all the trillions of connections between those billions of cells, there is always a tiny gap between the sending end of one cell and the receiving end of the next. The axon of one neuron stops just short of the dendrites of the next. The signal cannot simply jump across that gap as an electrical pulse. Something else has to happen, a different kind of signaling, a chemical kind, and that something else is one of the most important processes in the entire nervous system. We will spend our next section exploring that tiny gap, and the chemical messages that cross it, and the way the whole conversation between nerve cells depends on this brief, elegant transformation from electricity to chemistry and back again. But for now, let us simply rest with the image of the single nerve cell. A living tree in the quiet forest of the brain, roots reaching out to listen, a long, slender trunk carrying the message forward, branches at the far end passing the message on, and the whole thing wrapped, sometimes, in pale, fatty insulation that lets the signal race along at speed. This is the basic unit of everything we are going to talk about. The brain's 80-some billion neurons, the spinal cord's dense bundles of axons, the nerves that thread through the arms and legs. All of it, at root, is made of these cells, these trees, these quiet listeners and talkers, and the listening and the talking never stop. Even now, as you lie here in the dark, your neurons are active. Not all of them at once, that would be chaos, but millions of them, firing in complex patterns, maintaining the rhythm of your breath, the beat of your heart, the faint background awareness of the bed beneath you. The dendrites are receiving, the cell bodies are summing, the axons are sending, the myelin-wrapped cables are carrying signals at speed, and all of this is happening without you, without your effort, without your attention. The forest of the nervous system is alive with quiet, continuous activity, and you are carried within it, a passenger on a ship whose crew never sleeps. So the neuron is the first piece, the tree-shaped cell, the dendrites, the cell body, the axon, the fatty myelin wrapping that speeds the signal along, the 86 billion, roughly, such cells in the brain, each connected to many others, and the tiny gap between them, the space across which the signal must transform and leap. That gap is where we are going next. Not yet, not right away. For now, just let the image of the nerve cell settle. Let it drift in the back of your mind, a quiet shape, a tree with roots and branches, and a long, slender trunk, standing in the deep and peaceful dark of your own closed eyes. The tiny gap, that is where we are now. The space between one nerve cell and the next. The place where a signal arriving at the end of one axon must find a way to cross over and reach the dendrites of the cell that comes after it. And this crossing is not a simple leap. It is a transformation, a change of language, a shift from the electrical to the chemical, and then back to the electrical again. If the nervous system is a conversation, then this tiny gap is where the voice of one speaker is translated into something the next speaker can hear. We are going to spend some time here, in this quiet space between cells, because almost everything the nervous system does, every thought, every movement, every memory, every feeling, depends on what happens in this gap. The gap itself has a name, and I will give it to you now, but first let us picture it. Imagine two trees standing near each other in a forest. The branches of the first tree, those are the axon endings of the sending neuron, reach out but stop just short of the roots of the second tree. the dendrites of the receiving neuron. There is a narrow space between them, a sliver of open ground, so small that it can only be seen with the most powerful microscopes. That space, that tiny gap, is called a synapse. The word synapse comes from a Greek root that means to clasp or to join, which is a little misleading because the two cells do not actually join. They do not touch. They come very close, closer than anything else in the body, but they remain separate, with this small cleft of fluid between them. And this gap is crucial. It is not a flaw or a shortcoming. It is the very thing that allows the nervous system to be so flexible, so adjustable, so capable of learning and changing. Because the signal cannot simply race across the gap as an electrical pulse, the cell on the sending side has to release something into that space, a chemical substance that drifts across and delivers the message. That chemical substance is called a neurotransmitter, and the whole process of releasing it, having it cross the gap, and having it picked up by the receiving cell is one of the most elegant processes in the entire body. So let us walk through the steps of what happens at a synapse, slowly, one at a time. The electrical signal, the brief pulse that traveled all the way down the axon, arrives at the very end of the sending neuron. The end of the axon is not a single blunt tip. It branches into many small endings, like the twigs at the end of a branch, and each of those twigs swells into a tiny bulb. Inside each of those tiny bulbs, the neuron stores little packages of chemical messenger molecules, the neurotransmitters, waiting to be released. When the electrical signal arrives, it triggers those packages to move to the surface of the bulb and spill their contents out into the synaptic gap. The chemical messengers drift across the narrow space, a journey that takes only a fraction of a second. On the other side, the receiving neuron has receptors, which are like specially shaped docking stations built into its dendrites. The neurotransmitter molecules fit into these receptors the way a key fits into a lock, and when enough of them dock, they trigger a new electrical signal on the receiving side. The message has crossed. The electrical signal became a chemical signal in the gap, and then it became an electrical signal again in the next cell. This is the basic rhythm of communication in the nervous system. Electricity along the axon, chemistry across the synapse, electricity again along the next axon. And this happens trillions of times, all over your brain and body, every moment of every day and night. Right now, as you lie here, synapses are firing in the parts of your brain that process sound, letting you hear these words. Synapses are firing in the parts of your brainstem that control breathing, keeping your breath slow and steady. Synapses are firing in the pathways that maintain your muscle tone, holding your body in its resting shape. All of this is happening in the gaps between cells, in the quiet spaces where chemistry does its work. Now, the chemical messengers themselves, the neurotransmitters, come in many different kinds. The nervous system uses dozens of them, each with its own shape and its own general role, and the whole system is made more complex by the fact that a single neurotransmitter can have different effects depending on where it is released and which type of receptor it docks with. But there are a few neurotransmitters whose names are worth knowing, not because you need to memorize them, but because they come up so often in any conversation about the brain and the nervous system. We will name just a few of them here, and describe their well-established general roles, in the same calm and plain way we have been using. The first is dopamine. Dopamine is a neurotransmitter that is strongly linked to motivation, to reward, to the feeling of wanting to do something, and the satisfaction that comes from doing it. When you accomplish a small task, when you eat something you enjoy, when you anticipate something good, dopamine is part of the chemical signal that underpins that experience. It is not the only chemical involved, and the full story of motivation and pleasure is far more complex than any single neurotransmitter, but dopamine is a central player in that story. It is also involved in movement. The loss of dopamine-producing cells in one specific part of the brain is the main cause of the movement difficulties seen in Parkinson's disease. That is a well-established fact, and it connects the quiet chemistry of the synapse directly to the large-scale control of the body. The second neurotransmitter to name is serotonin. Serotonin is often linked to mood regulation and to the regulation of sleep. It is one of the chemical messengers that helps set the overall tone of the brain's activity, influencing whether a person feels calm and content or anxious and unsettled. Serotonin is also involved in the sleep-wake cycle, helping the brain transition between states of alertness and rest. Many of the most commonly prescribed antidepressant medications work by changing the way serotonin is handled at the synapse, slowing down the process by which it is reabsorbed after being released, so that it stays in the gap longer and has more opportunity to dock with receptors. That is a simplified description of a complex process, but the basic idea is that the medicine adjusts the chemical conversation, giving the message a little more time to be heard. The third neurotransmitter to name is acetylcholine. Acetylcholine is the chemical messenger used at the junction between nerves and muscles, the place where a motor neuron's axon meets a muscle fiber and tells it to contract. When you decide to move your hand, the signal travels down a motor neuron, reaches the synapse at the muscle, and acetylcholine is released into that gap. It docks with receptors on the muscle, and the muscle contracts. Acetylcholine is also used in many places within the brain itself, where it plays a role in attention and learning. But its role at the nerve-muscle junction is its most clearly defined job, and it is a good example of how the same basic mechanism, electrical signal, chemical release, receptor docking, new electrical signal, is used all over the body for many different purposes. Now, I want to pause here and note something that is genuinely calming, if you sit with it. The whole system I have just described, this cascade of electrical and chemical events, this release and docking and reuptake, is happening right now, in your own body, without you. You do not have to manage your dopamine levels. You do not have to consciously release acetylcholine at every muscle junction to keep yourself breathing. The system runs itself. The tiny packages of neurotransmitter are released when needed. The receptors dock. The signals cross. And you, the conscious you, the one lying in the dark listening to these words, are entirely free from having to supervise any of it. Medicines, as I mentioned, can adjust this system. Many common substances, from antidepressants to caffeine, work by changing the way neurotransmitters are released, or how long they stay in the gap, or how they bind to receptors. Caffeine, for example, works in part by blocking the action of a neurotransmitter called adenosine, which normally builds up during the day and promotes the feeling of sleepiness. By blocking adenosine's receptors, caffeine keeps the sleepiness signal from getting through as strongly, which is why it helps people feel more awake. That is a straightforward example of how a chemical from outside the body can step into the synaptic gap and change the conversation that is happening there. But I want to be honest with you about the limits of what is known. The fine details of how mood-related neurotransmitters actually shape emotion are still an active and unsettled area of research. We know that serotonin is involved in mood. We know that dopamine is involved in reward. But the exact chain of events that leads from a molecule of serotonin docking at a receptor to the felt experience of contentment or sadness, that chain is not fully mapped. The brain is not a simple chemical soup where more serotonin equals more happiness and less serotonin equals less. The reality is far more complex, with many different brain regions, many different receptor types, and many different interacting systems all playing a role. This uncertainty is not a failure of science. It is simply where the science currently stands, and it is fine, deeply fine, to sit with that uncertainty. You do not need to solve the puzzle of serotonin. Your brain is handling its own chemistry, in its own way, and the fact that researchers do not fully understand the details does not change the fact that the system is running, quietly and competently, as it always has. I want to return now to the image of the synapse itself, the tiny gap, because it is such a restful thing to picture. Two cells, very close, but not touching. A small space of fluid between them, molecules drifting across that space, released from one side, received on the other. A constant, gentle traffic of chemical messages, like notes passed between neighbors across a narrow alley, and the whole process is so small, so fast, so automatic, that you would never know it was happening if you were not told. Every thought you have ever had has involved synapses. Every memory you hold, every skill you have learned, every sensation you have felt, all of it passes through these tiny gaps, these quiet spaces between the trees. And the synapses themselves are not fixed. They can change. The sending side can release more or less neurotransmitter. The receiving side can add or remove receptors. The gap itself can widen or narrow slightly. This flexibility, this plasticity, is part of how learning works, how habits form, how the brain adapts to new experiences. We will talk about that more, much later, when we come to the section on memory and learning. For now, just know that the synapse is a living, adjustable thing, not a rigid connection but a soft and shifting one. So this is where we have arrived. From the single nerve cell, the tree with its roots and branches and long trunk, we have moved to the space between the trees, the gap where the conversation happens. The synapse, the release of neurotransmitter, the docking with receptors, the transformation of an electrical signal into a chemical one and back again. Dopamine, serotonin, acetylcholine, 3 chemical messengers among many, each with its own general role, each part of a system that is far more complex than any single name can capture. And behind all of it, the quiet fact that this system runs itself, without your effort, without your attention, a deep and ancient conversation happening in the dark of your own body. We are going to move next into the larger geography of the brain, the visible neighborhoods and regions that you would see if you could hold a human brain in your hands. But for now, just rest with the synapse. Rest with the image of those tiny bulbs at the ends of the axon branches, releasing their chemical messages into the gap. Rest with the image of the receptors on the other side, waiting like quiet docks for a ship to arrive. The whole nervous system is built on this moment, this crossing, this small and patient exchange. And it is happening right now, in you, in the dark, without a sound. Now we step back from the tiny gap, from the synapse and its chemical messengers, and we take a wider view. We are going to walk through the larger geography of the brain, the visible neighborhoods and regions that you would see if you could hold a human brain in your hands and turn it over slowly, looking at its shape from different angles. This is not an anatomy lesson to memorize. Think of it more like touring a quiet old house, walking from room to room, noticing what each room is used for, and then moving on. There is no need to remember which room is which. The names will be given, but the names are not the point. The point is just to walk through, slowly, and let the shape of the place become familiar in a soft and general way. If you were to look at a human brain, the first thing you would notice is its size, and its color, and its texture. It is about the size of 2 fists held together, and it is pale, a grayish pink, with a surface that is deeply folded and wrinkled. These wrinkles are one of the brain's most distinctive features, and we will come back to them in a moment, because they have their own quiet logic. But first, let us orient ourselves. The brain sits inside the skull, floating in a clear fluid that cushions it, and it can be divided, very broadly, into 3 main neighborhoods. 3 large regions, each with its own general set of jobs. The largest and most visible of these is the part that most people picture when they think of a brain, the great wrinkled dome that fills the top and front and sides of the skull. Then, tucked underneath and toward the back, there is a smaller, rounder structure that looks a bit like a miniature brain, also wrinkled but more tightly folded. And then, connecting the whole thing down toward the spinal cord, there is a narrow stalk, a kind of stem, that looks less like a brain and more like a thickened cable. These 3 regions, the large wrinkled dome, the smaller tucked-under ball, and the narrow connecting stalk, are the brain's main neighborhoods, and we will visit each one in turn. The large wrinkled dome is called the cerebrum. The cerebrum is by far the biggest part of the human brain, making up about 85% of its total weight, and it is the part responsible for most of what we think of as conscious mental life. It handles voluntary movement, the decision to lift a hand, to turn the head, to speak a word. It handles conscious sensation, the awareness of touch, of temperature, of the position of your limbs in space. It handles thought, language, planning, memory, reasoning, and the processing of information from the senses. The cerebrum is divided down the middle into two halves, the left and right cerebral hemispheres, which are connected by a thick bridge of nerve fibers that lets them share information. The left hemisphere generally controls the right side of the body and handles language in most people, while the right hemisphere generally controls the left side of the body and handles spatial awareness and certain aspects of attention. But this division of labor is not as clean as popular culture sometimes suggests. The two halves work together constantly, and almost any complex task draws on both sides. The surface of the cerebrum is a thin layer of densely packed neuron cell bodies, which gives it a slightly darker gray color, and this surface layer is often called gray matter. Beneath that surface layer, the deeper parts of the cerebrum are made mostly of axons, the long sending cables of the neurons, wrapped in the pale fatty myelin that we talked about earlier. This paler, deeper tissue is often called white matter. So the cerebrum is a wrinkled shell of gray matter wrapped around a core of white matter, a design that puts the processing cells on the outside where they have room to spread out and make connections. And that brings us to the wrinkles. The surface of the cerebrum is not smooth. It is folded into ridges and grooves, like a landscape of hills and valleys seen from very high up. These folds have names. The ridges, the raised parts, are called gyri, that is the plural, and a single ridge is a gyrus. The grooves, the valleys between the ridges, are called sulci, that is the plural, and a single groove is a sulcus. The reason the brain has these folds is simple and practical. The cerebral cortex, that thin outer layer of gray matter, where so much of the processing happens, needs to have a large surface area to hold all those billions of neurons and their connections. But the skull can only be so big, constrained by the size of the birth canal and the mechanics of walking upright. So the cortex folds in on itself, crumpling like a sheet of paper being pushed into a small box, packing a large surface into a small space. If you were to smooth out all the wrinkles of a human cerebral cortex and lay it flat, it would cover an area roughly the size of a pillowcase, perhaps 2.5 square feet. All of that processing surface is folded and tucked inside the bowl of the skull. The wrinkles are a space-saving measure, an elegant solution to a packaging problem. Now let us move to the second main neighborhood, the smaller structure tucked underneath the cerebrum at the back of the head. This is the cerebellum. The word cerebellum means little brain, which is a fair description of how it looks, a smaller, rounder, more tightly folded version of the big brain above it. The cerebellum sits just above the back of the neck, underneath the rear portion of the cerebrum. Its job, its well-established and primary job, is to coordinate movement. It does not initiate movement. The command to move a hand comes from the cerebrum, but the cerebellum smooths that movement out, adjusts it, compares the intended movement with what is actually happening, and corrects any errors in real time. It is the reason you can touch your fingertip to your nose with your eyes closed. It is the reason you can walk without consciously thinking about each shift of weight and angle of each joint. It handles balance, posture, and the fine motor coordination that makes movement fluid rather than jerky. The cerebellum, like the cerebrum, has a folded surface, but its folds are tighter and more regular, running in parallel ridges like the lines on a fingerprint. And despite its smaller size, it accounts for only about 10% of the brain's total volume. The cerebellum contains a remarkable number of neurons. In fact, it holds more than half of all the neurons in the entire brain, packed into that compact space at the back. Those neurons are arranged in a highly regular, almost crystalline pattern, which allows them to process information about movement with great speed and precision. People with damage to the cerebellum often have difficulty with balance and coordinated movement, not because they are weak or paralyzed, but because the fine-tuning mechanism that smooths out their actions is no longer working as it should. And then there is the third main neighborhood, the narrow stalk that connects the brain to the spinal cord. This is the brainstem. The brainstem is not large or dramatic to look at. It is a slender column of tissue at the base of the brain, just above where the spinal cord begins. But its small size hides its importance. The brainstem is responsible for the most fundamental, life-sustaining functions of the body, the jobs that must continue every moment of every day and night, whether you are awake or asleep, whether you are thinking about them or not. It controls breathing, it controls heart rate, it regulates blood pressure, it manages the sleep-wake cycle, it contains clusters of neurons that produce some of the key neurotransmitters we mentioned earlier, including serotonin and dopamine, and sends them out to other parts of the brain. The brainstem is the body's autopilot, the deep and ancient core that keeps the whole system running at the level below thought. The brainstem itself can be divided into smaller parts with names like the midbrain, the pons, and the medulla oblongata, but those names are more detailed than we need right now. The important thing to hold is the image, the cerebrum, large and wrinkled and domed, sitting on top. The cerebellum, smaller and rounder and tightly folded, tucked underneath at the back. And the brainstem, a narrow stalk, connecting everything down toward the spinal cord. 3 neighborhoods, 3 general sets of functions, thought and voluntary movement and sensation up top, smooth coordination and balance tucked behind, and the automatic, life-sustaining rhythms running through the narrow stalk below. I want to return now to something I mentioned in passing earlier, because it is one of those ideas that floats around in popular culture and can create a low-level sense of anxiety or inadequacy if it is not addressed. You have probably heard the claim that humans only use 10% of their brains. It is a very old idea, and it has been repeated in movies and books and casual conversation for decades. It is also false. Brain imaging studies, the kind where a person lies in a scanner and the machine tracks blood flow to different brain regions, show activity across nearly the entire brain over the course of a day. Not all at once, of course. If every neuron in your brain fired at the same moment, that would not be a sign of unused potential unlocking. That would be a seizure. The brain uses different regions at different times for different tasks. When you are resting with your eyes closed, a particular network of brain regions becomes active. When you are solving a problem, a different network engages. When you are moving, when you are listening, when you are remembering, different combinations of regions light up and then quiet down. Over the course of an ordinary day, just about every part of the brain sees some activity. There are no large, silent, unused regions waiting to be turned on. So if that old 10% idea has ever made you feel as though you are somehow not accessing your full capacity, as though there is a vast reservoir of hidden brain power you are failing to tap into, you can let that feeling go. It is not true. Your brain is working. It is working right now, as you lie here, in ways that are quiet and appropriate to this moment. It does not need to be working harder. It does not need to be more active. The activity it has right now, the gentle hum of the listening and resting brain, is exactly the right activity for this moment. And that is a restful thing to know. So we have walked through the 3 main neighborhoods of the brain. The cerebrum, the large wrinkled dome, handling thought and voluntary movement and conscious sensation. The cerebellum, the smaller folded structure tucked underneath, handling balance and smooth coordination. The brainstem, the narrow stalk, handling the automatic jobs like breathing and heart rate that never need your attention, and we have noted the wrinkles, the gyri and sulci, and the simple reason they exist, to pack a large surface of processing tissue into a small, bony container. And we have set aside, gently, the old myth about unused brain capacity. All of this sits inside the skull, warm and protected, floating in fluid, burning a steady supply of oxygen and glucose, running its quiet, continuous operations. And from the base of the brain, emerging from the brainstem, the spinal cord begins, the great trunk line that carries messages down from the brain to the body and up from the body to the brain. That is where we are going next. We are going to follow the spinal cord down the back, through the bony tunnel of the spine, and we are going to look at one of the clearest and most elegant examples of the nervous system in action, the reflex, the response that is faster than thought. But not yet. For now, just rest with the geography we have covered. The three neighborhoods, the wrinkled dome, the little brain, the narrow stalk. They are there, in the dark of your own skull, doing their work, and you do not need to supervise them at all. And so we follow the spinal cord now, down from the brainstem, through the bony tunnel of the spine, into the long central channel of the body. The spinal cord is the great trunk line, the main cable that connects the brain to nearly everything below the neck. It is not a separate thing from the brain. It is a continuation of it, an extension of the same tissue, running downward like a thick river of nerve fibers, and it is protected, carefully protected, by the series of bones that make up the spine. These bones are called vertebrae, and they are stacked one on top of another like a column of small, irregular rings. The spinal cord runs through the hollow center of those rings, suspended in fluid, wrapped in the same protective layers that surround the brain. The vertebrae give the spine its structure and its flexibility, letting us bend and twist, while the cord inside remains shielded from harm. The spinal cord itself is not very long compared to the rest of the body. In an adult, it is about 18 inches long, roughly the length of a forearm, and it is about as wide as a thumb at its thickest point. It stops partway down the back, around the level of the lower ribs, and from that point downward, only the branching nerves continue, fanning out like the tail of a horse. But despite its modest length, the spinal cord is one of the most densely packed information highways in the body. It carries millions of nerve fibers, bundled together, running in both directions at once. Some of those fibers are carrying sensory information upward, from the skin and muscles and joints toward the brain. Others are carrying motor commands downward, from the brain toward the muscles. The spinal cord is a two-way road, and the traffic never stops. The sensory fibers that run up the spinal cord bring the brain news of the body. They report on temperature, on touch, on pressure, on pain, on the position of the limbs in space. When your hand feels the coolness of the pillowcase, that information travels up sensory fibers in the spinal cord. When your back registers the soft pressure of the mattress, that too travels upward. All of the body's physical sensations, from the neck down, pass through the spinal cord on their way to the brain. The motor fibers that run down the spinal cord carry the brain's instructions outward. When you decide to shift your position slightly, to roll onto your side, to adjust the blanket, the command for that movement travels down motor fibers in the spinal cord, out through the branching nerves, and into the muscles that will carry out the action. Even the smallest movement, the slightest adjustment, involves this two-way flow of information through the cord. But the spinal cord is not just a passive cable, a simple conduit for signals passing up and down. It has its own processing capacity. It can make decisions, of a sort, without consulting the brain at all. And the clearest example of this, the one that appears in every textbook, and for good reason, is the reflex arc. The reflex arc is a simple, elegant circuit, and it illustrates something deeply calming about the way the nervous system works, which is that not everything needs to go all the way to the brain and back. Some things can be handled locally, quickly, by the spinal cord alone, and that local handling is part of what keeps the body safe. Let us walk through the classic example, the one you have almost certainly heard before. A hand touches a hot stove. The heat is intense enough to cause damage to the skin if the contact is prolonged. So what happens, in the first fraction of a second, is this. The heat activates specific sensory receptors in the skin of the fingertips, pain receptors and heat receptors, which we will talk about more when we come to the section on touch and temperature. Those receptors generate a signal, and that signal races along sensory nerve fibers up the arm, into the spinal cord at the level of the neck. Inside the spinal cord, that incoming sensory signal does two things. It sends a branch upward toward the brain, so that the brain will eventually become aware of the pain and the heat, but it also, and much more urgently, connects directly to motor neurons in the spinal cord through a very short, very fast circuit. The sensory neuron passes its signal to an interneuron, a small connecting neuron that lives entirely within the spinal cord, and that interneuron passes the signal straight on to a motor neuron. The motor neuron fires, sending a command back down the arm to the muscles that control the hand. The muscles contract. The hand pulls back. All of this happens before the signal traveling up to the brain has even arrived, before the brain has had time to register the sensation of heat, before the conscious thought, "That is hot, I should move my hand," has had a chance to form. This is why a reflex can feel faster than thought, because, in that first instant, the spinal cord has taken care of the problem before the brain even knew there was a problem. The conscious experience of pain, the ouch, the sharp awareness, the emotional reaction, arrives a split second later, once the signal has reached the brain and been processed. By then, the hand is already moving, already safe, because the spinal cord did not wait for permission. It acted, and it acted at a speed that conscious decision-making cannot match. This circuit, the reflex arc, is one of the simplest and most reliable circuits in the entire nervous system. It involves only a few cells, a sensory neuron, sometimes an interneuron, and a motor neuron, and the connections between them are direct and strong and fast. The signal does not need to navigate the vast, branching complexity of the brain. It takes a shortcut, a local route, and the result is a response that happens in a fraction of a second. The speed of a reflex like the hand withdrawal reflex is roughly on the order of a few hundredths of a second from stimulus to movement. Conscious reaction time, by comparison, is slower, more on the order of a few tenths of a second. The difference may sound small, but it is enough to prevent a burn, to catch a stumble, to blink before an object hits the eye. And there is something quietly reassuring in this arrangement. The body has built-in circuits for immediate protection, circuits that do not require your attention or your deliberation or your conscious effort. You do not need to decide to pull your hand back from something sharp. The decision is made for you, by a small loop of cells in your spinal cord, before you are even aware that a decision was needed. The system takes care of you at a level below thought. It is a kind of deep, embodied wisdom, an intelligence that does not belong to the conscious mind, but to the wiring itself. This is also why doctors sometimes test your reflexes during a checkup. You have probably had the experience of sitting on an examination table, legs dangling, while a doctor taps just below your kneecap with a small rubber hammer. That tap stretches a tendon in the knee, which activates a stretch receptor in the muscle, which sends a signal into the spinal cord, which connects directly to a motor neuron, which fires and causes the muscle to contract, which makes the lower leg kick forward slightly. That is the knee-jerk reflex, and it is a perfectly normal, healthy response. What the doctor is checking, by testing that reflex, is whether the circuit is intact, whether the sensory nerve is working, whether the spinal cord connection is functioning, whether the motor nerve is able to carry the command back to the muscle. If the reflex is absent, or if it is exaggerated, it can indicate a problem somewhere along that circuit. But for most people, most of the time, the reflex is just there, a quiet demonstration that the spinal cord is doing its job, routing signals locally, keeping the body's protective loops in working order. The reflex arc also illustrates something important about the relationship between the brain and the spinal cord. The brain, for all its complexity, does not micromanage every movement. It sets general goals and intentions, and it delegates. The spinal cord handles the details. When you walk, your brain decides to walk, sets the direction, adjusts for obstacles. But the rhythmic pattern of muscle contractions that actually moves your legs is generated by circuits in the spinal cord itself. These circuits are called central pattern generators, and they are another example of the spinal cord doing its own processing, running its own programs, without needing step-by-step instructions from above. The brain says walk, and the spinal cord knows how. This delegation is efficient. It frees up the brain to do other things, to think, to plan, to pay attention to the world around it, while the spinal cord manages the repetitive, well-practiced patterns of movement. So the spinal cord is more than a cable. It is a processing center in its own right, a local office that handles urgent matters on its own authority and manages routine tasks without needing to check with headquarters every time. It is the spinal cord that catches you when you stumble, that pulls your hand back from something hot, that keeps you breathing while you sleep. And all the while, it is relaying a constant stream of information up to the brain and a constant stream of commands back down, a two-way flow that never pauses, that has never paused since the moment the spinal cord first formed in the womb. And now, having followed the spinal cord down the back, we are ready to move outward. From the spinal cord, at regular intervals, pairs of nerves branch off and travel into the body. These are the peripheral nerves, the wiring that reaches everywhere else, the arms, the legs, the organs, the skin. The spinal cord is the trunk line, the peripheral nerves are the branches, and in the next section, we are going to follow those branches outward, into the far reaches of the body, and see where they go and what they do. But for now, just rest with the image of the spinal cord. A thick, pale bundle of fibers running down through the protective rings of the spine, carrying signals up and down, handling urgent matters on its own, keeping the body safe and coordinated and alive. It is working right now, as you lie here, even though you are still and quiet. It is working. It has always been working. And it requires nothing from you at all. And so we follow the branches now. The spinal cord, that great trunk line we have been resting with, does not keep its signals to itself. At regular intervals along its length, pairs of nerves peel away and travel outward, threading through the body like the roots of a tree spreading into the soil. These are the peripheral nerves, and together they make up what is called the peripheral nervous system. The word peripheral, as I mentioned way back at the beginning, simply means away from the center, out toward the edges, and that is exactly what these nerves do. They leave the central command post of the brain and spinal cord and venture out into the rest of the body, reaching the arms, the legs, the organs, the skin, every part of you that needs to sense the world or act upon it. The peripheral nervous system is not a separate thing from the central nervous system. It is continuous with it. The same neurons that have their cell bodies in the spinal cord send their axons out into the peripheral nerves. The same neurons that have their cell bodies out in the body send their axons into the spinal cord. The division between central and peripheral is a line we draw for convenience, but the tissue itself does not recognize a boundary. It is all one long, connected network, stretching from the top of the head to the tips of the toes and back again. Now, the nerves that make up the peripheral system can be sorted into two broad types, based on the direction their signals travel. Some nerves carry information from the body toward the brain and spinal cord. These are called sensory nerves or afferent nerves, though the word afferent is not one you need to hold on to. A sensory nerve is like a road leading into the city, bringing reports from the distant provinces. It might carry information about temperature, about touch, about pressure, about pain, about the position of a joint. All of that raw data streams inward, along the sensory nerves, toward the spinal cord and then up to the brain. The other type of nerve carries commands from the brain and spinal cord out toward the body. These are called motor nerves, or efferent nerves, again a word you can let go of as soon as it arrives. A motor nerve is like a road leading out of the city, carrying instructions to the muscles. It tells the muscle fibers when to contract, how strongly, for how long. When you decide to move your hand, the command travels down motor nerves. When your spinal cord triggers a reflex, the withdrawal command travels down motor nerves. Every movement you make, from the blink of an eye to the shifting of your weight in the bed, involves motor nerves carrying signals outward. Some peripheral nerves are purely sensory, carrying only incoming information. Some are purely motor, carrying only outgoing commands, but most are mixed, containing both sensory and motor fibers bundled together in the same cable. The nerve that runs to your hand, for example, carries sensory fibers that report touch and temperature from the skin, and it carries motor fibers that command the muscles of the fingers. The signals run in both directions along the same nerve, like two lanes of traffic on a single road, passing each other in opposite directions. There are many peripheral nerves in the human body, but there is one in particular that is worth dwelling on for a moment, because it is the longest and widest of them all, and because its name is familiar to many people who have never studied anatomy. This is the sciatic nerve. The sciatic nerve runs from the lower back, down through the buttock, down the back of the thigh, all the way to the foot. It is as thick as a finger in some places, a great cable of nerve fibers bundled together, and it carries both sensory and motor signals for much of the leg. It is the nerve that allows you to feel the ground beneath your feet and to command the muscles that move you forward when you walk. Because the sciatic nerve is so long and passes through so many tight spaces, between muscles, behind joints, through narrow channels in the pelvis, it is vulnerable to being pinched or compressed or irritated. When that happens, the result can be a condition many people know by the name sciatica, and sciatica illustrates something important about how peripheral nerves work. When a nerve is irritated at one point along its length, the pain or numbness or tingling that results is often felt not at the site of the irritation, but farther down the nerve's path, in the territory that nerve serves. A compressed sciatic nerve in the lower back can cause pain that shoots down the leg, through the calf, into the foot. The problem is in the back, but the sensation is in the leg. This is because the nerve's message is being disrupted along its length, and the brain interprets that disruption as coming from wherever the nerve's sensory endings are located. It is a misattribution, a kind of false report, and it is a reminder that what we feel is always a construction of the nervous system, not a direct readout of the body. This idea that a nerve can be pinched and cause symptoms far from the actual site of pressure applies to many peripheral nerves, not just the sciatic. The nerves that run through the wrist can be compressed, causing tingling in the fingers. The nerves that run through the neck can be irritated, causing pain down the arm. Wherever a peripheral nerve passes through a narrow space, there is a possibility of compression, and the symptoms will be felt downstream, in the territory that nerve serves. It is a strange feature of the system, but it makes sense once you understand that the nerve is a single long cable, and a disruption anywhere along that cable distorts the signal that arrives at the other end. Now, there is one more thing to say about peripheral nerves, and it is a gently hopeful thing. Unlike nerve tissue in the brain and spinal cord, which heals very poorly after damage, peripheral nerves have some ability to repair themselves. If a peripheral nerve is cut or crushed, the axon can sometimes regrow, sending out a new cable from the point of injury down toward its original target. This regrowth is slow, very slow, perhaps only a millimeter or two per day, which is about the thickness of a fingernail's growth in the same period. But over weeks and months, under the right conditions, a damaged peripheral nerve can sometimes find its way back, and sensation or movement can gradually return. This difference between peripheral nerves and central nerves is one of the more significant facts in all of neuroscience, and it has practical consequences. Damage to the spinal cord, which is part of the central nervous system, tends to be permanent, because the axons there do not regrow effectively. The reasons for this difference are complex and not fully understood, but they involve the environment the axons are growing through. Peripheral nerves are surrounded by cells that actively support regrowth. Central nerves are surrounded by cells that actively inhibit it. The same basic cell type, the neuron, has a very different capacity for healing depending on where it lives. It is a quiet reminder that context matters, in the body as in so many other things. So the peripheral nervous system is the great distribution network, the branching web of cables that carries sensation inward and commands outward. It reaches every part of the body that needs to feel or move. It is vulnerable to compression and injury, but it also carries within it a slow capacity for repair. And all of it, is connected back to the spinal cord, which routes the signals up to the brain, which makes sense of them and sends instructions back down. Right now, as you lie here, your peripheral nerves are active. The sensory nerves in your skin are reporting the pressure of the bed, the temperature of the room, the texture of the fabric against you. The motor nerves are maintaining a gentle tone in your muscles, keeping your body in its resting shape. The sciatic nerve, that great cable running down each leg, is quiet but ready, carrying no urgent signals, just the steady background hum of a system in standby. And all of this activity is happening below the level of your attention, without your effort, without your worry. The peripheral nerves are doing their job, and you do not need to supervise them at all. We are going to move next into a different kind of peripheral nerve, the kind that does not report to your conscious mind at all, the kind that runs the automatic background functions of the body. These are the nerves of the autonomic nervous system, and they govern the beating of your heart, the rhythm of your breath, the quiet work of your digestion. That is where we are heading, but for now, just rest with the image of the branching nerves, the long pale cables threading through the body, carrying sensation inward and commands outward, a quiet two-way traffic that has been running since before you were born and will continue running long after you fall asleep tonight. And now we come to the part of the nervous system that never asks for your attention, that never rises to the level of conscious thought, that runs the deep and steady rhythms of the body while you sleep and while you wake. This is the autonomic nervous system, and of all the topics we have walked through so far, this one may be the most genuinely confusing in its naming, but also the most directly calming in its implications. Because the autonomic nervous system is, in a very real sense, the part of you that takes care of you. It is the background crew, the silent engine room, the part of the nervous system that manages the heart, the lungs, the blood vessels, the digestive organs, the pupils of the eyes, the sweat glands, and a dozen other functions that must continue every moment, without fail, and without your conscious input. The word autonomic shares a root with the word automatic, and that is a good way to think about it. The autonomic nervous system runs automatically. You do not need to tell your heart to beat. You do not need to tell your lungs to draw breath. You do not need to tell your stomach to begin the slow work of digestion after a meal. All of these things are handled by the autonomic nervous system, working quietly in the background, adjusting its output moment by moment to meet the body's changing needs. And the way it does this is by having two branches, two modes, that pull the body in slightly different directions. These two branches are called the sympathetic nervous system and the parasympathetic nervous system, and they are not opponents so much as partners, working together to keep the body in balance. Let us start with the sympathetic branch. The sympathetic nervous system is often described, in shorthand, as the fight or flight system. That phrase captures something true, but it is a little too dramatic for our purposes. A calmer way to think about the sympathetic branch is that it is the system that prepares the body for action. Any kind of action, not just fighting or fleeing, but also standing up, walking, concentrating on a task, responding to a stressor, or simply waking up in the morning. When the sympathetic branch is more active, the heart beats a little faster, the breathing becomes a little quicker and a little deeper. Blood is directed away from the digestive organs and toward the muscles, where it will be needed if action is required. The pupils of the eyes widen slightly, letting in more light. Sweat glands become more active, ready to cool the body if it heats up from exertion. All of these changes happen together as a coordinated package, preparing the body to move, to act, to engage with the world. The sympathetic nerves that trigger these changes emerge from the spinal cord in the middle part of the back, the thoracic and upper lumbar regions, and they connect to a chain of small processing stations called ganglia that run alongside the spine. From those stations, the signals fan out to the organs and tissues they control. The sympathetic system uses a particular set of chemical messengers, primarily adrenaline and a closely related substance called noradrenaline, to get its signals across. These are the chemicals that surge during moments of high arousal or stress, but they are also present at lower levels throughout the day, keeping the body in a state of gentle readiness. Now let us turn to the other branch, the parasympathetic nervous system. If the sympathetic branch is the system of action, the parasympathetic branch is the system of rest. It is often called the rest and digest system, and that phrase captures its essence more peacefully. When the parasympathetic branch is more active, the heart rate slows, breathing becomes slower and more relaxed. Blood returns to the digestive organs, and digestion proceeds comfortably. The pupils of the eyes constrict, the muscles relax, the body shifts from a state of readiness to a state of restoration. This is the mode the body enters after a meal, during quiet relaxation, and, importantly for our purposes, during sleep. The parasympathetic nerves take a different route than the sympathetic ones. Many of them travel along a single, very important nerve that runs directly from the brainstem down into the chest and abdomen. This nerve is called the vagus nerve, and it is one of the most significant nerves in the entire autonomic system. The vagus nerve carries parasympathetic signals to the heart, the lungs, the stomach, the intestines, and other organs. It is a wandering nerve. The word vagus actually means wandering in Latin, and it meanders through the body like a slow river, touching many different organs along its path. When the vagus nerve is active, it gently slows the heart and encourages digestion, and it plays a central role in the calming response that helps the body settle into rest. And here is a fact that is worth pausing on, because it is directly useful to you in this very moment. A slow, deep exhale activates the parasympathetic branch through the vagus nerve. This is not a metaphor, it is a physiological fact. When you breathe out slowly and fully, the vagus nerve sends signals that gently lower the heart rate. The sympathetic activity dials down a notch, and the parasympathetic activity dials up. You can feel this if you pay attention. Take a slow breath in, and then let it out even more slowly, and you may notice a subtle settling, a slight softening of tension. That is the parasympathetic nervous system at work. That is the vagus nerve doing its quiet job. And you do not need to force anything. You do not need to breathe in any special pattern. Just knowing that a slow exhale tips the balance toward calm is enough. Your body already knows how to do this. It has been doing it every night of your life. Now, I want to be careful about a common misunderstanding. The two branches of the autonomic nervous system are often talked about as if they are an on-off switch, sympathetic on, parasympathetic off, or vice versa. But that is not how the system actually works. It works more like a dimmer switch, or perhaps like two hands gently adjusting a dial in opposite directions. Both branches are always active to some degree. What changes is the balance between them, the relative level of activity on each side. During the day, the sympathetic tone is generally a little higher, keeping the body alert and ready. During the night, during sleep, the parasympathetic tone becomes more dominant, letting the body slow down and restore itself. But there is never a moment when one branch is completely off. The system is constantly adjusting, constantly fine-tuning, moment by moment, in response to what the body needs. This is why it is more helpful to think of the autonomic nervous system as a balancing act, rather than a binary switch. The sympathetic and parasympathetic branches are not enemies. They are partners in a continuous dance, pushing and pulling gently, keeping the body's internal environment stable and appropriate to the situation. The heart does not simply beat at one speed all day and another speed all night. It varies, beat by beat, in response to the shifting balance of sympathetic and parasympathetic input. This variability is a sign of health. A heart that can speed up when needed and slow down when at rest is a heart that is responsive and well-regulated. And that regulation is handled entirely by the autonomic nervous system without your conscious intervention. The autonomic nervous system also illustrates something we touched on earlier, which is that the nervous system is not just about the brain telling the body what to do. Much of the information flows in the other direction as well. The organs send signals back to the brain through autonomic nerves, reporting on their state, their needs, their current conditions. The brain integrates this information and adjusts the autonomic output accordingly. It is a feedback loop, a conversation, and it never stops. Even now, as you lie here, your blood pressure is being monitored by sensors in your arteries, and your autonomic nervous system is adjusting your heart rate and the diameter of your blood vessels to keep that pressure steady. Your body temperature is being monitored, and your autonomic system is adjusting blood flow to the skin and sweat gland activity to keep you comfortably warm. All of this is happening below the surface, below the level of thought, a continuous and competent management of the body's internal world. So the two modes are these: the sympathetic branch, preparing the body for action, and the parasympathetic branch, settling the body back into rest. Both are necessary. Both are always active to some degree. And right now, in this quiet moment, as you lie in the dark with your eyes closed, the balance is naturally tipping toward the parasympathetic side. Your heart rate is slowing, your breathing is deepening, your muscles are softening, the vagus nerve is active, carrying its calming signals to your organs. Your body is doing what it knows how to do. It is settling, it is restoring, it is preparing, in its own quiet way, for sleep. We are going to move next into the senses, into the way the nervous system registers the outside world, the touch of the sheets, the temperature of the air, the faint sounds in the room. But for now, just rest with the idea of these two modes, these two branches, this gentle balancing act that never requires your attention. The sympathetic system that wakes you up and the parasympathetic system that settles you down. The vagus nerve wandering through the body, carrying its slow and calming messages. And the simple, restful fact that a slow exhale tips the balance, just a little, just enough, toward the quiet and the dark and the deep. And so we come to the senses, to the way the nervous system reaches out and touches the world. We have spent time with the deep interior of the body, the brain, the spinal cord, the branching nerves, the two modes of the autonomic system. But now we turn outward, to the surface, to the place where the body meets everything that is not the body, the skin. The skin is not just a covering. It is a sensory organ, the largest one we have, and it is threaded through with nerve endings that are tuned to different aspects of the physical world. Some of these nerve endings respond to light touch, some respond to pressure, some respond to vibration, some respond to heat, some to cold, and some to pain. Together, they give the brain a continuous, detailed report on what is happening at the boundary between the self and the surroundings. These sensory receptors are not scattered evenly across the body. Some places have a much higher density of them than others, and the difference in density explains something you already know from ordinary experience. Your fingertips are far more sensitive to fine detail than your back is. Your lips are even more sensitive than your fingertips. If you close your eyes and touch something, the edge of a blanket, the surface of a pillow, the texture of a sheet, your fingertips can tell you an extraordinary amount about that surface, whether it is rough or smooth, warm or cool, soft or stiff. This is because the skin of the fingertips is packed with sensory receptors, thousands of them in a space no larger than a postage stamp. Each of those receptors sends its own signal up through the peripheral nerves, into the spinal cord, and onto the brain, and the brain weaves all those signals together into a single, rich impression of the object being touched. The back, by contrast, has far fewer receptors spread over a much larger area. If someone were to trace a shape on the skin of your back, you might have trouble identifying it, not because there is anything wrong with your back, but simply because the sensory map there is lower in resolution, like a photograph made of fewer dots. This unevenness is not a flaw, it is a practical design. The parts of the body that do the most detailed exploratory work, the hands, the lips, the tongue, are given the highest resolution sensory equipment. The parts that serve more as background, as general surfaces, the back, the thighs, the upper arms, are given lower resolution equipment, which is perfectly adequate for their role. The nervous system allocates its resources where they are needed most, and it does so without any conscious planning, simply through the way the body develops in the womb and in early childhood. The different types of receptors in the skin are each tuned to a particular kind of stimulus. Some are sensitive to very light touch, like the brush of a feather or the movement of a single hair. These are located just beneath the surface of the skin, and they fire rapidly when something first makes contact, then quiet down if the contact is sustained. They are good at detecting change, at alerting the brain that something new is happening on the skin. Other receptors are sensitive to sustained pressure, to the steady indentation of the skin that happens when you press your finger against a surface or when the weight of your body presses into the mattress. These receptors keep firing as long as the pressure is present, giving the brain a continuous sense of how firmly the skin is being touched. Still, other receptors are sensitive to vibration. These are located deeper in the skin, and they respond best to rapid, repetitive movements. The buzz of a phone, the hum of a motor, the textured surface of a road felt through the soles of the feet. And then there are the receptors for temperature. Separate receptors detect heat and cold, and they work together to give the brain a sense of the thermal environment. When the air is cool, the cold receptors fire more. When the air is warm, the warmth receptors fire more. These signals do not just tell you what the temperature is, they also feed into the autonomic nervous system, helping the body decide whether to shunt blood toward the skin to release heat or pull blood away from the skin to conserve it. And then there are the receptors for pain. Pain receptors, also called nociceptors, a word you do not need to remember, are nerve endings whose entire job is to detect things that might cause damage. Intense heat, intense cold, strong pressure, sharp objects, certain chemicals released by injured cells. When these receptors are activated, they send signals along specific nerve fibers that are different from the ones that carry ordinary touch. These pain fibers are often thinner and slower than the fibers for light touch, which is part of why pain can have a different quality, a dull, aching, lingering quality compared to the quick, precise sensation of a light touch. But some pain fibers are fast, carrying the sharp, immediate signal that makes you pull your hand back before you even know why. These fast pain fibers are the ones involved in the reflex arc we talked about earlier. The slow pain fibers are the ones that produce the deeper, longer-lasting ache that sets in after an injury, the kind of pain that is less about immediate escape and more about protecting the injured area while it heals. Pain is a protective alarm system. That is its fundamental purpose. It exists to tell the brain that something in the body may be in danger of damage or has already been damaged, and that action should be taken to prevent further harm. People who are born without the ability to feel pain, a very rare condition, often suffer serious injuries and infections because they do not get the warning signals that tell the rest of us to shift our weight, to pull away from something sharp, to rest an injured joint. Pain is unpleasant by design, because an alarm that was pleasant would not be an effective alarm. But the unpleasantness of pain is not fixed. It can be modulated, turned up or turned down, by the brain and the spinal cord themselves. This is one of the more important things to understand about pain, and it is also one of the areas where the science is genuinely still unfolding. The brain does not simply receive pain signals and play them back like a recording. It interprets them, it adjusts them. It can dampen them or amplify them depending on the context. The same physical injury can feel very different depending on whether a person is frightened or calm, distracted or focused on the pain, in a safe environment or a threatening one. This is not imagination. It is a real physiological process. The brain and spinal cord have pathways that can release natural pain-suppressing chemicals, endorphins and other substances, that act like a dimmer switch on the incoming pain signals. These pathways can be activated by exercise, by deep relaxation, by certain kinds of touch, and perhaps by the body's own internal state. The existence of these pathways is well established, but the exact way the brain constructs the subjective feeling of pain, the raw, felt experience of hurting, from the combination of incoming signals and internal modulation, is still not fully understood. Researchers continue to study it, and the not knowing is simply where the science currently stands. This is restful to sit with, if you let it be. Pain is not a simple, direct readout of tissue damage. It is a complex, constructed experience, shaped by many factors, and the brain has its own ways of managing it. You do not need to understand the mechanism. You do not need to figure it out. The system is running in its own imperfect way, and your job in this quiet moment is simply to rest. Now, as you lie here, your skin is doing all of this work without your attention. The pressure receptors are reporting the weight of your body against the bed. The temperature receptors are noting the coolness or warmth of the air. The touch receptors are registering the texture of the fabric against you. And all of these signals are streaming inward, up the peripheral nerves, through the spinal cord, into the brain, where they are woven together into the quiet, comfortable awareness of being held by the bed, supported, safe. None of this requires your effort. None of this requires your thought. The sensory system is working, quietly and continuously, just as it has been doing since the day you were born. We are going to move next into two of the most familiar senses, sight and hearing, and the specific nerves that carry those signals into the brain. But for now, just rest with the skin, with the quiet hum of sensation that surrounds you like a gentle field. The fingertips, so dense with receptors, are resting now, doing little work, just reporting the soft pressure of the blanket. The back, with its lower resolution map, is reporting the broad, diffuse sensation of support. The body is comfortable, the sensory system is calm, and you, the one lying here, do not need to do anything at all except let the sensations come and go, like waves on a shore, like the slow and steady breath of the body at rest. Now we turn to sight and hearing, the two senses that most people name first when they think about how the body connects to the world. They are different from touch in an important way. Touch is spread across the whole body, a diffuse and ever-present sense that covers every inch of skin. Sight and hearing are concentrated in specific organs, the eyes and the ears, and they rely on dedicated nerves that carry their signals directly into the brain. These nerves are among the most important cables in the whole nervous system, and they each have their own quiet, elegant way of turning the physical world into something the brain can understand. Let us begin with sight, with the eyes and the nerve that serves them. Light enters the eye through the pupil, passes through the clear lens, and falls onto a thin sheet of light-sensitive cells at the back of the eye. This sheet is called the retina, and it is not just a passive screen. It is a piece of the brain itself, pushed out into the eye during early development, and it does a considerable amount of processing before the signal ever leaves the eye. The retina contains two main types of light-sensitive cells, named for their shapes. There are rods, which are long and thin and highly sensitive to dim light, and there are cones, which are shorter and rounder and responsible for color vision and fine detail. Rods do not detect color, they detect brightness and movement, and they allow us to see in near darkness, though the vision they provide is blurry and monochrome. Cones need more light to work, but they give us the sharp, colorful view of the world that we think of as normal daytime vision. When light hits these cells, it triggers a chemical change, and that change generates an electrical signal. That signal passes through several layers of processing cells within the retina. Cells that sharpen edges, that detect motion, that compare neighboring patches of light and dark. And then it converges onto a single exit point at the back of each eye. All of the processed visual information from that eye funnels into a thick bundle of nerve fibers that exits the back of the eye and travels toward the brain. This bundle is the optic nerve. Each eye has its own optic nerve, and the two optic nerves meet just behind the eyes at a crossover point where some of the fibers from each side swap over to the opposite side of the brain. This crossover means that the left half of the visual world, as seen by both eyes, is processed by the right side of the brain, and the right half of the visual world is processed by the left side of the brain. It is an elegant arrangement, and it happens automatically, without any conscious awareness that the signals have been split and rerouted. Now there is a detail about the optic nerve and the brain's visual processing that is worth dwelling on, because it is one of those quiet facts that can settle in the mind like a small, smooth stone. The lens of the eye is curved, and like any curved lens, it bends light in a way that flips the image upside down. The light from the top of a scene hits the bottom of the retina, and the light from the bottom of the scene hits the top. The world, as it is projected onto the back of your eye, is inverted. It arrives at the brain upside down, and the brain, without any effort from you, without any instruction, without you even knowing it is happening, flips the image back. It takes the inverted signal and turns it right side up so that the world appears correctly oriented. This is not a trick or an illusion. It is simply the way the visual system works, and it has been doing it every waking moment of your life. You have never seen the world upside down, even though the raw data entering your brain is inverted, because the brain corrects it before you ever become aware of it. This flipping is a reminder, a gentle one, that what we see is not a direct photograph of the world. It is a construction, built by the brain from the raw materials provided by the eyes. The retina detects patterns of light and dark and color. The optic nerve carries those patterns to the brain. The brain sorts, flips, sharpens, compares, and integrates the signals, and what we experience as vision is the finished product, seamless and immediate, and apparently effortless. But beneath that seamlessness is an enormous amount of work, done by billions of neurons in the retina, the optic nerves, and the visual processing regions at the back of the cerebrum. All of it is automatic. All of it is invisible to conscious thought. You open your eyes and the world is simply there, already assembled, already right side up, already meaningful. Now let us turn to hearing, to the ears and the nerve that serves them. Sound is vibration. It is waves of pressure moving through the air, rippling outward from whatever made the sound. A voice, a rustle of fabric, the distant hum of a refrigerator. The outer ear catches these waves and funnels them down the ear canal to the eardrum, a thin membrane that vibrates in response. On the other side of the eardrum, 3 tiny bones, the smallest bones in the human body, pick up the vibration and pass it along, amplifying it slightly to a fluid-filled, spiral-shaped structure deep inside the ear. This structure is the cochlea, and it is here that the real magic of hearing takes place. Inside the cochlea, running along its spiral length, is a thin ribbon of tissue lined with tiny hair cells. These are not hairs like the ones on your head. They are microscopic, and they are called hair cells because each one has a small tuft of hair-like projections sticking up from its surface. When sound vibrations travel through the fluid of the cochlea, they cause these hair-like projections to bend. The bending triggers the hair cell to fire, sending an electrical signal. Different hair cells are tuned to different frequencies of vibration. High-pitched sounds bend the hair cells near the start of the spiral, and low-pitched sounds bend the hair cells farther along. The signals from all of these hair cells converge into a single nerve, which carries the combined information out of the inner ear and into the brainstem. This nerve is the auditory nerve, and it is the pathway by which everything we hear, every voice, every note of music, every rustle and breath and distant sound, reaches the brain. The auditory nerve carries its signals to the brainstem, and from there the information passes through several relay stations, crossing over to both sides of the brain, until it reaches the auditory processing regions in the temporal lobes of the cerebrum. There, the brain sorts the signals into recognizable patterns, speech, music, noise, silence, and weaves them into the continuous stream of conscious experience. And all of this happens in real time, with a speed and precision that allows us to locate a sound in space, to understand a spoken sentence, to recognize a familiar voice in a crowded room. There is a quiet sadness to the hair cells of the inner ear, and it is worth mentioning here, not as a source of alarm, but simply as a fact to sit with. In humans, once these hair cells are damaged or destroyed, they do not grow back. Loud noise, prolonged exposure to sound above a certain volume can kill them. Certain medicines can damage them. Age wears them away, and when they are gone, the hearing loss that results is permanent. This is why people who work in loud environments wear hearing protection. It is why a lifetime of loud concerts or headphones turned up too high can gradually erode the ability to hear high frequencies. The hair cells are delicate, and they do not regenerate the way skin cells or liver cells do. The body has many capacities for repair, but this is not one of them. I mention this not to create worry, but because sound and hearing are especially fitting to dwell on in a sleep-focused episode like this one. Right now, as you lie here, your auditory system is still working. Your ears are still catching whatever faint sounds are present in the room. The hum of the heating or cooling system, the distant sound of traffic or wind, the soft sound of this voice. Your hair cells are still bending in response to those vibrations, still sending signals along the auditory nerve, still feeding the brain with a quiet stream of auditory information. And soon, when you fall asleep, that stream will continue, but the brain will process it differently, filtering out the irrelevant sounds, letting you sleep through the ordinary nighttime noises while still remaining alert enough to wake you if something truly unusual or urgent occurs. The auditory system never fully shuts down. It is always listening, always vigilant, a quiet sentinel in the dark. So we have walked through the two great sensory nerves, the optic and the auditory, and the pathways they take from the eyes and ears into the brain. Sight, with its upside-down images and its rods and cones and its silent automatic correction. Hearing, with its vibrating eardrum and its tiny bones and its delicate, irreplaceable hair cells. Both senses are active now, to whatever degree the darkness and quiet of the room allow. Your eyes are closed, so the optic nerve is carrying a minimal signal, mostly the soft red-black darkness of light filtered through closed eyelids. Your ears are still open, still receiving, still carrying the gentle sound of a voice talking slowly in the quiet. Both systems are working, without effort, without cost, without you needing to manage them at all. We are going to move next into a topic that often causes confusion when people talk about the brain, the idea of neuroplasticity, of the brain's ability to change and learn and adapt. But for now, just rest with the senses. Rest with the quiet knowledge that your body is receiving the world, even now, even in the dark. The soft pressure of the bed on your skin, the faint sounds of the night, the gentle darkness behind your closed eyes, all of it is flowing inward, through the nerves, through the synapses, into the quiet processing rooms of the brain. And you, the one lying here, do not need to do anything but let it flow. We have walked through the senses, through the nerves that carry sight and sound into the brain, and now we arrive at one of the most talked about and most often misunderstood ideas in all of neuroscience. The idea that the brain can change. The idea that the nervous system is not fixed, not rigid, not set in stone once childhood ends, but is instead something more like a living landscape, continuously reshaped by use and experience. This idea has a name, and that name is neuroplasticity. It is a word that gets used a great deal, in many different contexts, and with many different claims attached to it. Some of those claims are true. Some of them are hopeful in ways that outpace the evidence, and some of them are simply the result of a good and useful concept being stretched too far. So we are going to spend some unhurried time with this idea, clearing up confusion rather than adding to it, and letting the science speak in its own calm, measured voice. Let us start with the plainest possible definition. Neuroplasticity, sometimes just called plasticity, is the ability of the nervous system to change and adjust its connections over time in response to experience. That is the core idea. The brain you have today is not exactly the same brain you had yesterday, and it will not be exactly the same brain tomorrow. The changes are small, and they happen slowly, but they are real. When you learn something new, a fact, a skill, a route through a familiar place, The physical connections between certain neurons in your brain become stronger. The synapses, those tiny gaps we talked about earlier, become more efficient at passing signals. The sending side may release more neurotransmitter, or the receiving side may add more receptors, or both. The result is that the pathway is more likely to fire again in the future. A pathway that fires together, wires together. That is a simple phrase that captures a deep truth about how the brain adapts. This strengthening of connections is not a metaphor. It is a physical process. The cells involved are changing the number and distribution of the proteins that make up the synapse. The receiving dendrites can even grow small protrusions, called dendritic spines, that increase the surface area available for making connections. These spines can appear and disappear over the course of hours and days, reflecting the brain's ongoing adjustment to the demands placed on it. When you practice a musical instrument, the brain regions that control the fine movements of your fingers undergo measurable changes. The area of the motor cortex devoted to those fingers expands slightly. When you learn a second language, the regions involved in processing speech sounds and generating sentences strengthen their connections. When a London taxi driver spends years learning the city's vast street network, a famously demanding test of spatial memory known as the knowledge, the part of their brain involved in spatial navigation, the hippocampus, actually grows measurably larger. These are well-documented findings, and they illustrate that the brain is genuinely responsive to sustained, repeated experience. But, and this is where the confusion often begins, neuroplasticity does not mean that the brain can rewire itself instantly or limitlessly. It is not a magic wand. It is not a guarantee that any injury can be healed, or any limitation can be overcome simply by trying hard enough or thinking positive thoughts. The phrase, "the brain can rewire itself," is often used in ways that suggest a kind of infinite flexibility, as if the brain were made of soft clay that could be molded into any shape at any time. That is not accurate. The brain has structure. It has regions that are specialized for particular functions. The visual cortex at the back of the brain is built to process visual information, and while it can adapt somewhat if a person is blind from birth, taking on other sensory processing tasks, for example, this adaptability has limits. It is not the case that any part of the brain can learn to do any job equally well. The brain is plastic, yes, but it is not infinitely plastic. It is more like a landscape that can be gradually reshaped by the slow forces of wind and water than like a lump of clay that can be instantly remolded by hand. Meaningful change in the brain happens gradually, through repetition. It is not the result of a single experience or a single decision. It is the result of doing something over and over again, day after day, week after week. This is why learning a new skill takes time. It is why breaking an old habit takes time. The brain is not resisting change. It is simply built to change slowly, conservatively, preserving what has worked in the past while cautiously adjusting to new demands. This conservatism is a feature, not a bug. A brain that rewired itself instantly in response to every new experience would be a brain that could not hold on to anything. It would lose old skills as quickly as it gained new ones. The slowness of plasticity is what allows us to accumulate knowledge and expertise over a lifetime, building layer upon layer of strengthened connections, without losing the foundations. And there is another important limit to understand. Most of the brain's adaptability comes from changing existing connections, not from growing many new neurons. For a long time, it was believed that the adult brain produced no new neurons at all, that we were born with all the neurons we would ever have, and that the number could only decrease over time. That picture has been revised somewhat in recent decades. We now know that new neurons do continue to be born in a few specific regions of the adult brain, most notably in a part of the hippocampus, a structure deep in the temporal lobe that is crucial for certain kinds of memory. This process is called adult neurogenesis, and it is a genuine and well-documented phenomenon. But it is limited. It happens in only a small number of places, and the number of new neurons produced is modest compared to the billions already present. The vast majority of the brain's plasticity, its ability to learn, to adapt, to recover from injury, comes not from adding new cells, but from strengthening, weakening, and reorganizing the connections between existing cells. The tree-shaped neurons we described earlier, with their dendrites and axons and synapses, are constantly adjusting the strength and number of their connections. But the trees themselves, for the most part, are the same trees you have had since childhood. This is a calming thought in its own way. The brain is stable, it is reliable, it is not in a constant state of upheaval. The core architecture that makes you who you are, the deep patterns of connection that underlie your personality, your memories, your ways of thinking and feeling, does not vanish overnight. It persists, it provides continuity. And yet, within that stable framework, there is room for growth. There is room for learning. There is room for the slow, patient accumulation of new skills and new knowledge. The brain is both steady and flexible, like a tree that keeps its trunk and main branches while continually putting out new leaves and letting old ones fall. Now we come to memory, which is one of the most direct expressions of neuroplasticity. When you form a memory, you are physically changing your brain. The experience you have, a conversation, a view from a window, a moment of understanding, triggers a pattern of neural activity. That pattern, if it is strong enough or repeated enough, leaves a physical trace. The synapses involved in that pattern become strengthened. The connection between those particular neurons becomes more likely to fire together again. And later, when something reminds you of that experience, the same pattern is reactivated, and you experience the memory. This much is well established. The strengthening of synaptic connections in response to activity is one of the most reliable findings in all of neuroscience, studied in organisms from sea slugs to humans. But, and this is a genuinely important but, exactly how a specific memory is physically stored and retrieved is still an open question in neuroscience. We know that the hippocampus is crucial for forming new memories of events and facts. We know that damage to the hippocampus can leave a person unable to form new long-term memories while still able to learn new skills, which tells us that different kinds of memory rely on different brain systems. We know that memories are not stored in a single location, like a file on a computer, but are distributed across networks of neurons. A memory of a childhood birthday party might involve neurons in the visual cortex that process the sights, neurons in the auditory cortex that process the sounds, neurons in the emotional centers that process the feelings, and neurons in the hippocampus that bound them all together into a single coherent episode. But how, exactly, that distributed network encodes the specific details of that specific party, the color of the balloons, the taste of the cake, the face of a friend, and how the brain manages to retrieve that exact pattern years or decades later is not fully understood. The physical basis of memory, the code by which neurons represent specific experiences, remains one of the great open questions in the study of the brain. And that not knowing is simply where the science currently stands. It is not a cause for frustration or alarm. It is, if anything, a cause for humility and wonder. The brain is so complex, so densely interconnected, that even the act of remembering your own name involves processes that are still being worked out. You do not need to understand those processes to use them. You do not need to know how memory works to have a memory. The system runs, and it runs beautifully, even as the researchers continue to study its deepest mechanisms. You can lie here in the dark, and you can remember the events of the day, or the face of someone you love, or the sound of a favorite piece of music, and all of it will come to you effortlessly, carried by physical processes that are still partly mysterious. The mystery does not diminish the experience, it deepens it. And here, in this quiet moment, memory and plasticity are not demands. They are not tasks you need to perform. You are not required to learn anything right now. You are not required to strengthen any synapses or grow any dendritic spines. The brain is doing what it does, maintaining its connections, consolidating the experiences of the day, preparing for the work of sleep, Learning and memory will still be there tomorrow. Right now, the only thing to do is rest and let the brain take care of itself. It knows how. It has been doing it for your whole life. So this is the shape of neuroplasticity. The brain changes. It changes slowly, through repetition. It changes mostly by adjusting existing connections, not by growing many new cells. It changes in response to experience, to practice, to attention. And those changes are what allow us to learn, to remember, to grow. But the changes are not infinite. The brain is not infinitely rewirable. It is a living organ with a deep and enduring structure, and that structure is part of what makes us who we are. The plasticity and the stability go together, two sides of the same coin, two aspects of the same quiet, ongoing process of being alive. We are going to move next into the topic that sits closest to your own present moment, sleep. What the nervous system does when you drift off, how the brain transitions from waking to sleeping, and what is known and not known about the purpose of the hours you spend in the dark. But for now, just rest with the idea that your brain is gently, quietly changing. The day's experiences are settling into place. The connections that matter are being ever so slightly strengthened. The ones that do not matter are being ever so slightly pruned. And all of this is happening without your effort, without your attention, in the deep and patient quiet of the night. And now we come to the topic that sits closest to your own present moment, sleep. The thing you are drifting toward, the thing your body is already beginning to do, whether you are aware of it or not. We have walked through the nervous system from its smallest parts to its largest structures, from the single nerve cell out to the branching pathways that reach every corner of the body, and now we arrive at the state toward which this whole journey has been quietly tending. Sleep is not simply the absence of wakefulness. It is not simply the brain shutting off or powering down. Sleep is an active process, a carefully orchestrated transition that involves specific brain regions, specific chemical signals, and a shift in the balance of the autonomic nervous system. It is something the brain does, not something that merely happens to it. And the doing of it, the falling asleep, is one of the most intricate and still not fully understood processes in all of neuroscience. Let us begin with the transition itself, the moment of falling asleep. What actually happens in the brain as you drift from wakefulness into sleep? During the day, while you are awake and alert, certain regions of the brain are actively keeping you in that state. Deep in the brainstem, there are clusters of neurons that produce arousal signals, chemical messages that radiate outward to the rest of the brain and keep it in a state of readiness. These arousal centers send their signals up into the cerebrum, the large wrinkled dome we talked about earlier, and those signals keep the cortex in a state of activation that supports conscious awareness, attention, and the processing of sensory information. As long as those arousal centers are firing strongly, you remain awake. The world feels present, your thoughts feel sharp, your senses are tuned to the outside. But as the day wears on, and as the evening approaches, a different set of signals begins to build. A chemical called adenosine accumulates in the brain during waking hours. Adenosine is a byproduct of the brain's energy use, and as it builds up, it creates a kind of sleep pressure, a gentle but growing inclination toward rest. This is one of the reasons you feel progressively more tired as the day goes on. Caffeine, as we mentioned earlier, works by blocking adenosine's receptors, temporarily preventing that sleep pressure from being felt. But adenosine continues to build regardless, and when the caffeine wears off, the accumulated pressure comes rushing back, often felt as a wave of tiredness. Meanwhile, a small structure deep in the brain called the hypothalamus, which sits just above the brainstem, is keeping track of the body's internal clock. The hypothalamus contains a cluster of cells called the suprachiasmatic nucleus, a name you do not need to hold on to, that receives signals from the eyes about the presence or absence of light. When the light fades, when evening comes and the world grows dark, this internal clock signals another part of the hypothalamus to release a hormone called melatonin. Melatonin does not cause sleep directly, but it helps prepare the body for sleep. lowering alertness and signaling to the various systems that night has arrived. As adenosine builds and melatonin rises, the balance of activity in the brain begins to shift. The arousal centers in the brainstem receive inhibitory signals, quieting signals, from other parts of the brain. The firing of those wakefulness-promoting neurons slows down. As they slow, their stimulating effect on the cerebrum diminishes. The cortex begins to settle. The rapid, desynchronized electrical activity of wakefulness gives way to slower, more synchronized rhythms. And gradually, almost imperceptibly, the brain transitions from the state of being awake to the state of being asleep. This is not a single moment, not a switch being flipped. It is a gradual process, a slow tipping of the balance, and it can take many minutes. You may be aware of it happening, or you may not. Most people do not remember the exact moment they fall asleep, because the brain systems involved in forming memories are themselves part of what is changing as sleep begins. Once sleep takes hold, the brain does not simply go quiet. It cycles through a series of stages, each with its own characteristic pattern of electrical activity. The early stages of sleep are light, and the brain waves slow down but remain somewhat irregular. As sleep deepens, the brain waves become slower and more synchronized, entering what is called slow-wave sleep or deep sleep. This is the stage during which the brain is least responsive to outside stimuli, the stage from which it is most difficult to wake someone. And then, periodically throughout the night, the brain enters a very different kind of sleep, one in which the electrical activity looks almost like wakefulness. The eyes move rapidly beneath closed lids. The body's muscles, with a few exceptions, are temporarily paralyzed. This is rapid eye movement sleep, or REM sleep, and it is during this stage that the most vivid dreams tend to occur. The brain cycles through these stages roughly every 90 minutes or so, moving from light sleep into deep sleep and back again, with periods of REM sleep growing longer as the night progresses. A full night's sleep in a healthy adult typically includes 4 or 5 of these cycles. The architecture of sleep, the particular pattern of stages and their duration, is not random. It is shaped by the brain's own internal rhythms, and it appears to serve important functions, though not all of those functions are fully understood. One of the things that happens during sleep is a shift in the autonomic nervous system. During the day, the sympathetic branch, the action branch, tends to be more active, keeping the body alert and ready. During sleep, particularly during deep sleep, the parasympathetic branch becomes more dominant. The heart rate slows, the breathing becomes slower and more regular, blood pressure drops, digestion proceeds at its own quiet pace. The body enters a state of restoration and repair. This is part of why sleep feels restorative. It is not just the brain that rests. The whole body, under the influence of the parasympathetic nervous system, dials down its activity and turns inward, conserving energy, repairing tissues, clearing away waste products that have accumulated during the day. And this brings us to one of the most interesting and still evolving areas of sleep research: the relationship between sleep and memory. It is now well established that certain memory-related processes are supported during sleep. During deep sleep, the brain appears to replay patterns of neural activity that were first generated during waking experience. The hippocampus, that structure deep in the temporal lobe that is crucial for forming new memories, communicates with the cortex during sleep, and this communication is thought to help consolidate memories, strengthening the synaptic connections that represent important experiences and pruning away the ones that are less important. It is as if the brain, during the quiet hours of the night, is sorting through the events of the day, deciding what to keep and what to let go, weaving the important threads into the larger tapestry of long-term memory. REM sleep, the stage of vivid dreaming, appears to play a different but complementary role. It has been linked to emotional processing, to creative association, to the integration of new information with old. Some researchers believe that REM sleep helps the brain make novel connections between seemingly unrelated ideas, which may be part of why we sometimes wake with a solution to a problem that had seemed insoluble the night before. But this is still an area of active investigation, and the exact role of REM sleep in memory and cognition is not settled. Now, having said all of this, I want to be honest about something. The full purpose of sleep is still not completely understood. This may seem surprising, given how universal sleep is. Every animal that has been carefully studied sleeps in some form. Even animals as simple as fruit flies have periods of rest that resemble sleep. If sleep were not essential, evolution would have done away with it long ago, because a sleeping animal is vulnerable, unable to watch for predators or search for food. The fact that sleep has been conserved across hundreds of millions of years of evolution tells us that it serves functions that are absolutely necessary for survival. And yet, despite decades of research, scientists cannot say with certainty what those functions are. There are theories, and many of them have strong evidence behind them. Sleep likely serves multiple purposes. It conserves energy. It clears metabolic waste products from the brain. It consolidates memory. It restores the body's tissues. It regulates mood and emotional resilience. It supports immune function. But exactly which of these functions is the essential one, the one that makes sleep non-negotiable for life, is still not known. And that not knowing is not a problem. It is not something to solve or worry about. It is simply where the science stands. The brain has been putting itself to sleep every night for your entire life, and it has never needed you to understand how it works in order to do it well. You do not need to know why sleep exists in order to fall asleep. The process is happening, right now, whether you are analyzing it or not. The adenosine is building. The melatonin is rising. The arousal centers in your brainstem are beginning to quiet down. The parasympathetic nervous system is gently taking the helm. Your heart rate is slowing, your breathing is deepening, your muscles are softening into the mattress. All of this is happening without your effort, without your attention, without your consent or control. So let the pacing slow here, because this section sits closest to your own present moment. This is not abstract neuroscience anymore. This is what is happening in your own body, right now, as you lie in the dark. The transition from waking to sleeping is underway. The brain is doing what it knows how to do. The nervous system, that vast and intricate network we have been walking through, is settling into its nighttime mode. The sympathetic branch is dialing down. The parasympathetic branch is dialing up. The vagus nerve is carrying its calming signals to your heart and your lungs and your digestive organs. The brainstem is reducing its arousal output. The cerebrum, that great wrinkled dome of thought and sensation, is quieting, its electrical rhythms slowing, its attention turning inward, away from the outside world, toward the deep interior of sleep. And you, the one lying here, do not need to do anything at all. You do not need to try to fall asleep. Trying is counterproductive. Sleep is not an achievement. It is not a task to complete. It is a natural process, an ancient rhythm, and your body knows how to do it. It has been doing it since before you were born. You can let go of the effort. You can let go of the need to understand. You can simply lie here, breathing slowly, and let the nervous system do what it has always done, what it will always do, carrying you gently from wakefulness into the quiet and the dark and the deep. We are going to finish with a very soft landing. No new facts, no new ideas. Just a gentle circling back over the ground we have covered, spoken more slowly and more sparsely, letting the words trail off into the quiet. But for now, just rest here. Rest in the knowledge that your body is preparing for sleep. The machinery is working, the systems are running, and you, the passenger on this quiet ship, are being carried toward the night. And so we arrive at the final stretch, the quiet drift-off close, the part of the journey where we stop moving forward and simply rest where we are. There will be no new facts now, no new names to learn, no new structures to visit, no new processes to understand. The tour is complete. What remains is only a soft circling back, a gentle revisiting of the ground we have covered, spoken more slowly and more sparsely, so that the words themselves can begin to fade into the background of your awareness, like the last notes of a song that does not so much end as dissolve into silence. We began, a long while ago now, with the smallest living piece of the whole system, the single nerve cell, the neuron, the tree-shaped cell with its roots and its branches and its long, slender trunk, the dendrites reaching out to receive, the cell body summing up the signals, the axon carrying the message forward, sometimes wrapped in its pale, fatty insulation, the myelin, that lets the signal race along its speed. And we noted, quietly, that the human brain contains roughly 86 billion of these cells, a number so large it is hard to feel the weight of it, a number that does not need to be remembered, only acknowledged, like the number of stars in a dark sky. Each of those billions of cells is connected to hundreds or thousands of others, forming a network of almost unimaginable density, and that network is what you are. Not in a metaphorical sense, in a literal, physical sense. The patterns of connection between your neurons, the particular strengths of your particular synapses, the unique architecture of your own brain, these are the physical basis of everything you have ever thought or felt or remembered or been. From the single cell, we move to the space between cells, the tiny gap, the synapse, where the electrical signal becomes a chemical one and then becomes electrical again, the release of neurotransmitter into that narrow space, the docking with receptors on the other side, the quiet traffic of chemical messages that never stops. Dopamine, serotonin, acetylcholine, 3 messengers among many, each with its own general role, each part of a conversation that is far more complex than any single name can capture, and we noted that many things about this conversation are still not fully understood, and that not knowing is restful, not alarming. The system runs. It has always run. It does not need you to understand it in order to do its work. Then we stepped back and looked at the larger geography of the brain itself, the 3 main neighborhoods. The cerebrum, the great wrinkled dome, handling thought and voluntary movement and conscious sensation, its surface folded into ridges and grooves to pack a vast area of processing tissue into the small bowl of the skull. The cerebellum, the little brain tucked underneath at the back, handling balance and smooth coordination, packed with more than half of all the brain's neurons despite its small size. And the brainstem, the narrow stalk connecting brain to spinal cord, handling the automatic jobs that never need your attention, breathing, heart rate, the rhythm of wakefulness and sleep. 3 neighborhoods, each with its own character, all of them working together in ways that are still being mapped. From the brain we followed the spinal cord down the back, through the bony tunnel of the vertebrae, that great trunk line of nerve fibers carrying sensory information upward and motor commands downward. And we paused on the reflex arc, that elegant local circuit that can pull your hand back from something hot before the brain even knows what has happened. The spinal cord acting on its own authority, handling urgent matters without waiting for permission from above. The reflex that is faster than thought, because in that first instant, it is. A reminder that the body takes care of you at a level below consciousness, that there are protective circuits built into your wiring that do not require your attention or your effort or your consent. From the spinal cord we moved outward into the peripheral nerves, the branching cables that reach everywhere else. The sensory nerves carrying information inward from the skin and muscles and joints. The motor nerves carrying commands outward to the muscles. The sciatic nerve, that great cable running from the lower back down through the leg, vulnerable to compression and capable, under the right conditions, of slow repair. The peripheral nerves, unlike their central counterparts, have some ability to heal and regrow, a quiet capacity for renewal that the brain and spinal cord do not share. A reminder that different parts of the system have different rules, different strengths, and different vulnerabilities. Then we turn to the autonomic nervous system, that silent background manager of the body's internal world. The 2 branches, the 2 modes, working not as an on-off switch but as a dimmer, constantly adjusting the balance between action and rest. The sympathetic branch, preparing the body for movement and effort and engagement with the world. The parasympathetic branch, settling the body back down, slowing the heart, deepening the breath, resuming the quiet work of digestion and repair. And the vagus nerve, that wandering nerve that carries the parasympathetic signals to so many organs, activated by the simple, ancient act of a slow exhale. A reminder that the body has a built-in calming system and that you can access it, gently and without effort, simply by breathing out. From the autonomic system, we move to the senses, to the way the nervous system registers the outside world. The skin, the largest sensory organ, packed with receptors tuned to touch and pressure and vibration and heat and cold and pain. The fingertips, so dense with receptors, capable of extraordinary discrimination. The back, with its lower resolution map, reporting the broad diffuse sensation of support. The pain system, that protective alarm, modulated by the brain and spinal cord in ways that are still not fully understood. And the two great sensory nerves, the optic nerve carrying the upside-down image from the eye to the brain, where it is silently flipped right side up, and the auditory nerve carrying the vibrations from the delicate, irreplaceable hair cells of the inner ear. Sight and sound, the two senses that most people name first, each with its own dedicated pathway, each working without effort, without cost, without the need for conscious supervision. We spent time with memory and learning, with the confusing idea of neuroplasticity, the brain's ability to change, slowly, through repetition, by strengthening the connections between neurons that fire together. The physical basis of learning, the dendritic spines growing and retracting, the synapses becoming more or less efficient. And the limits of that plasticity, the fact that the brain is not infinitely rewirable, that meaningful change takes time and effort, that the core architecture persists, and the open question of how, exactly, a specific memory is physically stored, how the pattern of a particular experience is encoded in the connections between cells and retrieved years or decades later. Still not fully understood, still an open door, still a quiet mystery at the heart of who we are. And then we came to sleep, to the process that is happening in your own body right now, as you lie here in the dark. The arousal centers in the brainstem quieting down, the adenosine building, the melatonin rising, the hypothalamus tracking the body's internal clock, the gradual, almost imperceptible transition from waking to sleeping, a slow tipping of the balance rather than a switch being flipped. The cycles of the night, the slow waves of deep sleep, the rapid eye movements of dreaming, the parasympathetic nervous system taking the helm, heart rate slowing, breathing deepening, the body entering its state of restoration and repair, and the honest acknowledgement that the full purpose of sleep is still not completely understood, even after all these years of study. The body does it anyway. The brain does it anyway. It has been doing it every night of your life, and it does not need you to understand why. All of this, every part of this long, slow walk through the nervous system, has been happening in your own body, without your effort, without your attention, while you listened. The neurons have been firing. The synapses have been releasing their chemical messages. The spinal cord has been relaying its signals. The peripheral nerves have been carrying sensation inward and commands outward. The autonomic system has been adjusting the balance, moment by moment, keeping the heart beating, the lungs breathing, the digestion proceeding at its own quiet pace. The sensory receptors in your skin have been reporting the pressure of the bed, the temperature of the room, the texture of the fabric against you. Your ears have been catching the sound of this voice and turning it into nerve signals and sending those signals into your brain, where they have been processed into words and meaning. And soon, very soon now, those same systems will carry you the rest of the way into sleep. The parasympathetic branch is active now. The vagus nerve is doing its quiet work. Your heart rate is slow and steady. Your breathing is deep and regular. Your muscles are soft and heavy against the mattress. The arousal centers in your brainstem are dialing down, one by one, letting the cortex settle into its slower rhythms. The balance is tipping, gently, inexorably, toward rest. And you do not need to do anything to make this happen. You do not need to try. You do not need to effort. You do not need to understand. the system is running. It has always been running. It will continue to run while you sleep, and it will be there when you wake, ready for another day. Think of it this way: if thinking is still happening, the nervous system is like a calm and competent crew managing a ship. You are the passenger, resting below deck. The crew knows what to do. They have been doing it for years, for decades, since before you were born. They do not need your instructions. They do not need your supervision. They need only your trust, your willingness to let go of the wheel and let them work. And right now, in this quiet moment, that trust is all that is being asked of you. Let the crew work. Let the ship sail. Let the night carry you where it will. The slow exhale, the vagus nerve, the parasympathetic calm. These are not just ideas anymore. They are what is happening in your own body, right now, with every breath you take. You do not need to breathe in any special way. Your body already knows how to breathe. It has been breathing since the moment you were born, and it will continue breathing all through the night. But if you like, you can notice the exhale. You can let it be a little slower, a little fuller. And with each exhale, the balance tips just a little further toward rest. The heart slows, just a fraction. The muscles soften just a little more. The mind quiets, just a little deeper. The words are thinning out now. The sentences are becoming shorter. There is less to say, and less need to say it. The journey is complete. The walk through the nervous system has reached its end. What remains is only the quiet and the dark and the slow, steady rhythm of your own breath. The tree-shaped cells are still there, in the dark of your skull, still connected, still firing, still doing their ancient work. The synapses are still releasing their chemical messages. The spinal cord is still relaying its signals. The peripheral nerves are still carrying sensation inward, even now, even as the brain begins to pay less attention to what they report. The autonomic system is still balancing, still adjusting, still keeping the body in its gentle nighttime equilibrium. All of it is running, all of it is working, and none of it requires anything from you. So let go. Let the words go. Let the effort go. Let the day go. Whatever happened today, whatever will happen tomorrow, it does not matter now. Right now, there is only this moment, this breath, this quiet, this slow drift into the dark. Your body knows how to sleep. It has always known. Let it. Just let it. The bed is holding you. The night is holding you. The nervous system, that vast and intricate network, is holding you. And you do not need to do anything at all. Just breathe and drift.